Hello everyone, my name is Arun Sharma and I'm the instructor for the course today, and I welcome you all to session 2 of today is utilizing numerical analysis for foundation design. And Midas holds the copyrights to this presentation. So this means that I can sue you if you use this presentation without our consent. But if you ask, then we'll most likely accept your request. The learning objectives for this session. So at the end of this course, participants will be able to understand analysis. They'll be able to understand unique benefits of numerical analysis and applications of numerical analysis through case studies on various foundation types. During this session, we'll be having quizzes after every chapter. We'll have 3 quizzes after chapter 1, chapter 2, and chapter 3. So we'll first start with the background of the foundation, and we'll focus on deep foundations and pile foundation. Then we'll discuss pile raft foundation in detail under chapter 2, and then we'll move on to chapter 3, where we will be covering why numerical analysis is necessary for pile foundations. And towards the end, we'll be discussing about some project applications where numerical analysis was used for modeling or analyzing different types of foundations. So let's begin with chapter 1, which is the background, where I'll be covering about the type of foundations, introduction to pile analysis, types of deep foundations, and the load resistance of deep foundations. So as we all know, foundation can be broadly classified into 2 headings, shallow foundation and deep foundation. And then shallow foundation can be further divided into 2 types of foundations, footing or mat. And under footing foundations, we have different types, individual, continuous, or combined. Then under deep foundation, the classification is as per pile, pier or drill shaft, and caisson foundations. And deep foundation is the focus of our session today. So in the beginning, I'll briefly talk about piles, pile groups, and pile raft foundation. And here you can see this is the quotation from Dr. Bridge Das. And by the way, I'm pretty sure most of you already know this eminent geotechnical expert. He is the author of several geotechnical engineering textbooks that we study in our colleges, and engineers use these handbooks for their geotechnical design work. He has also authored several research papers which are still treated as pretty standards for handling any geotechnical problem till date. So he once said, although numerous investigation, both theoretical and experimental, have been conducted in the past to predict the behavior and the load-bearing capacities of the pile and its mechanism, it has not yet been fully understood, and it may never be. So let's see why Dr. Das thinks so. So because pile foundation, although they are structurally speaking not a complex structure, but their interaction and the soil around them leads to so many uncertainties that their behavior is always unknown. So each case of deep foundation could be treated as an independent case, and their complexities in the interaction leads to engineers performing several research and discussing about it in the different platforms and podiums. So in a nutshell, the behavior of pile itself is not complex, but its interaction with soil and the soil behavior itself makes it complex and unknown. So now that we know that the behavior of pile foundation is unknown or it's complex, so let's see why and where we must use deep foundations. And I might be repeating this for most of you in the class today, but it might be helpful for some engineers who are still new to deep foundations. So if you are working on soft soil near the surface, you will need deep foundation to carry your load to the stable strata. If you are working with soil layers that have collapsible or expansive soil, that means there is a huge uplift force, then you need deep foundations. If you are working in conditions where there are high lateral loads, you need deep foundations. If the force exerted by the superstructure is eccentric to the center of gravity of the structure or of the foundation, it can cause tilting effects. In these scenarios, you need deep foundations. Then if you are working with foundations in riverbed, where there could be huge scouring and the piles could be exposed above the ground surface. So again, this represents an unstable or irritable strata. Therefore, we need deep foundations. If you're working on a structure where the foundation is close to an excavation site and this could lead to its stability risk, we need deep foundation. Or if the superstructure is exerting a very heavy load that needs to be transferred to a much stable layer, you need a multiple pile system or deep foundation. Then let's see what are the different types of deep foundations. So based on material, we have steel pile, concrete pile, and timber pile. And as we all know, the most commonly used pile are concrete piles. And the reason for using concrete piles is that it is kind of stronger than timber and cheaper than steel. But nevertheless, when we are estimating the cost of pile foundation or deep foundation, it is not just the material that determines the cost. It is also the drilling that you have to do, and how you have to do, and how many drilling you have to do. So all that cost adds to the cost to the construction. And therefore, if you are using numerical analysis, you are able to estimate the true strength of the material, true interaction between soil and structure, and the true behavior of the soil, therefore allowing you to fully optimize the strength of the material. And in many cases it has been found that you could reduce the number of piles under a foundation if you are fully optimizing the strength of the concrete of the pile. Now that being said, let's see what are the other classifications. Like I said, methods of installation differ, and this goes to affect the bearing capacities of the pile. So if you have a driven pile, it is considered as a separate system altogether. Or if you're working on a bored pile or screwed pile, the behavior differs. Then let's see what is the other classification. The other classification is as per the effect of installation of the pile. So the piles could be displacement piles or could be non-displacement piles. Displacement piles are piles where you allow certain mobilization in the piles, whereas non-displacement piles are on rigid strata that don't that are not mobilized at all. Now, if you have any questions about these classifications, you can raise your hand. I can explain further or take your questions. Otherwise, I'll consider this to be affirmative, that you are very clear with the classifications of deep foundations. Thank you. So in order to understand why deep foundations are preferred at the aforementioned conditions, we must understand the load transfer mechanism of a pile. So to start with, let's see what are the components of a pile. So you see at the top we have the pile head, at the base we have pile tip. The vertical member of the pile is called pile shaft, which has certain diameter, let's say, or width b, and the length of the shaft is called pile length, and usually denoted by alphabet L. So when the load is applied on top of this pile, the entire structure is mobilized and resists the movement. Now the resistance is largely offered by the skin of the shaft, so we call it skin friction. And depending upon the stable strata you have, you can expect the resistance from the base also. So this type of base resistance is also called end bearing resistance. So a pile can be designed as skin friction pile or end bearing resistance pile, or a combination of both, depending upon the layout of the pile, the dimensions, the material of the pile, the external load that is applied onto the pile, so, and the method that is adopted to install that pile. So this brings us to the end of chapter 1, and let's quickly summarize what we learned today. So pile foundation behavior is hard to predict because of the soil pile interaction and the complex soil behavior. Unstable soil strata need deep foundation to safely carry load to harder or stable layer. Structures exerting loads like high lateral load, tilting, or very heavy vertical loads, or structures near excavation sites risking the stability, require deep foundation. And load transfer in pile takes place through skin friction from pile shaft and end bearing resistance from the pile base. And piles could be designed as skin friction, end bearing, or a combination of both depending upon soil condition, method of installation, pile material, and external load. Now we have summarized chapter 1. We'll have a quiz that will have 3 questions. The duration is 5 minutes, and I'll be launching it now on your screens. You have to select the right answers based on the instructions provided along with the question. And I'll resume the session once 5 minutes are over. Thank you. One more minute to go. Alright, I think the test is over now. So everyone has submitted the result, and let's resume with the presentation. I hope you guys did well. So let's move on to chapter 2, where we'll be covering pile foundation design methods. We'll be covering single pile, group of piles, and pile raft foundations. So when we start for pile analysis with single pile, we start with bearing capacity assessment, and I'm sure everyone in the room must be familiar with these formulations and symbols. So you can see the bearing capacity, ultimate bearing capacity of the pile is a summation of the shaft resistance and tip resistance. Now if you're working on skin friction pile, then you would have just the shaft resistant component and not the tip resistant. And if it's an end bearing pile, then it will just have the end bearing component, not the skin friction. And as you can see, the skin friction or the shaft resistance is dependent upon the kind of soil you are using. So you can use a different, depending on different type of soil layer, you will have either the coefficient of addition or coefficient of skin friction that is to be used. And for tip resistance, you can see QT times AT, which is the tip resistance times the area of the tip. Now, based on this fundamental theory, numerous theoretical and empirical formulas have been developed considering the various variables in the field below. So based on soil type, whether you are working in cohesive or non-cohesive soil, you are working with the rock strata or soil strata, the formulations are different. Then based on the installation method, that's what I mentioned in the previous chapter 2. If it's a driven pile or if it is a cast in place pile. And based on the pile material also, because if you're using concrete, you will have different coefficient roughness of the skin. If you're using steel, it will have a different behavior. So based on these parameters, we have a different formulation setup. Then let's talk about settlement. As you can see, settlement of a pile is comprised of three types of settlement. S1, which is the elastic settlement. This means when the load is applied, the material, no matter if it's concrete or steel, will undergo elastic settlement. Then S2, which is the shaft settlement. So based on the load applied, the shaft will displace related to the surrounding soil strata. And then we have S3, which is the tip settlement. That is the overall pile will settle down from the ground level or from the pile cap location. So the summation of these three types of settlements is need to be assessed in order to determine what is the settlement for the pile. Then the most important thing that you need to determine for a pile is the lateral behavior. And for that we have two main categories here, which are based on something like an empirical formula, like Brom's method, where this factor beta is applied in order to determine the lateral behavior of the pile. And the formulation, as you can see, is kd times 4 ei to the power 1 by 4. So this means you need to have these variables punched in, where k is the coefficient of horizontal subgrade reaction, d is the diameter or the width of the pile that needs to be applied, and this formula keeps changing depending upon different pile types, different conditions, and different diameters or different lengths of the pile. So it has certain other branches. But most popular method, and I'm sure everyone must be knowing this method, it's called PY analysis. And certain points to be noted about PY analysis, that we have different types of PY curves for each and every layer. And then in order to do the analysis, we want to simulate the behavior of this soil layer using a non-linear spring. So when it comes to performing the analysis, you need two things. First, which is a pile, which is formed of divided beam elements. So for each layer we have let's say beam 1, beam 2, beam 3, or beam 4, or beam A, beam B, beam C, beam D. Then we have soil that is represented with the nonlinear springs, which where we use the PY curves as the input parameters. So let's quickly go over this PY analysis process. So first step is you have to calculate the deflection of each pile segment. So every segment you'll apply a PL, which is a lateral load, and check what is the displacement that is occurring, or deflection that is occurring. Then depending upon the deflection, you have to calculate how much resistance the soil is offering based on the PY curve you have. And then these deflections and soil pressures, as you can see from the PY curve, are interrelated. So sometimes it might happen that you get a deflection which is exceeding the pile resistance value, or the soil resistance value. So you need to do several iterations till you find the arrangement which depicts your PY curve as obtained from the field. So you have to keep doing the iterations in order to obtain the correct value or the correct behavior that you can rely upon. And this method of PY analysis is actually based on finite difference method. Now, since this session is more geared towards numerical analysis, let's see this alternate approach of numerical analysis. How is it compared to PY analysis? So here you can see a quick comparison. So let's start with soil behavior. So under PY curve or PY analysis, we use PY curves to determine or represent the soil behavior. Whereas in numerical analysis, we use constitutive models that are based on realistic data and represent the soil more accurately than approximate PY curves and using springs. Then for pile elements, under PY analysis we use beam, whereas in the numerical analysis you can use a solid or a beam member, and this beam member could be linear as well as non-linear. So by non-linear we mean that you can also model the non-linear behavior of the steel or the concrete that is being used to use as a material for the pile. And this goes to increase the accuracy of the analysis and more accurately represents the realistic scenario. Then when you are creating the model under PY analysis, you are dealing with a set of beams and nonlinear springs, whereas under numerical analysis you are actually dealing with a 2D or 3D environment of a structural model, where you'll have the real soil strata represented by a constitutive material model, the pile member represented by a 2D or 3D member with linear or non-linear material properties. And then in order to simulate the soil structure interaction, it is purely based on the PY curve under PY analysis, and hence the name PY analysis. Whereas in numerical analysis, you can have certain set of interface or embedded elements to capture this effect. And again, as we know, we in PY curves are based on your field test, which is very realistic data. But in order to simulate this in a software program, you have to do several iterations in order to achieve this behavior. Whereas in numerical analysis, the number of iterations are way less as compared to PY curve, and the results are more accurate and easily obtained. Then let's say you have to incorporate the superstructure or the upper structure in interaction with the substructure. So there are not many solutions out there that take into account the superstructure behavior while doing PY analysis. There is one which is called FB Peer. I'm sure if you must have used it somewhere down your career path. But if you are using a numerical analysis approach, then you're more than welcome to create your entire superstructure, not just limited to the pile cap. You can have your pier, you can have your superstructure on top of it, and see the interaction between the superstructure and substructure. Then let's say your D foundation is adjacent to another structure's foundation, or there is an excavation site. Then this PY analysis is not able to incorporate the effects of the adjacent structures onto your pile foundation. Or if you're doing this pile foundation, what effect will it have on the adjacent structure, which is possible only through numerical analysis approach. And as we all know, soil undergoes consolidation. It has a stress history. As in when you are constructing, you are excavating for deep foundations, you are adding or removing load. Therefore, the stresses are either relieved or added. So all those kinds of variables that come in on site cannot be captured by PY analysis. For that, you must do a numerical analysis. And when we look at the design application, you must be thinking that I'm being so anti-PY analysis right from the beginning. Well, it's not like that. PY analysis is found useful. We have been using it all throughout. But it is useful for our conventional projects. But as in when we move on from a conventional layout to a more complex layout, or if we are put under the pressure to optimize the design and make the project more economical, then we need to go for numerical analysis. And the tools that are available in the industry for PY analysis are LPile, FBP, or LT-Base, which are pretty standard software for performing PY analysis and come with different limitations, as you can see here. On the other hand, for numerical analysis, we have softwares like Midas GTS, FLAC, or Plaxis, and they are all able to perform numerical analysis and lead to a more refined result. Then let's talk about group of piles or pile groups. Never you will see that the piles are standing alone by itself. Not commonly though, but what is more common is that piles are actually applied in a group, and the pile heads are connected with a thick pile cap. Now the role of pile cap is to take the load from the superstructure and redistribute it on the substructures or on the pile evenly. And for getting this pile layout correct or optimizing this group effect, what we have to really work out is what is the optimal layout of the pile. What diameter of pile should I use in this group? What should be the thickness of my pile cap. So there are so many variables that you have to really work with in order to optimize the group behavior of the pile. So certain facts about pile groups. The ultimate capacity of pile may not be equal to the number of piles multiplied by the capacity of a single pile. And the ratio of the pile group capacity, that is, let's say the ultimate capacity of the piles is let's say 450, and the total capacity of the piles, let's say you have 5 pile and each pile ultimate capacity is 100, so the total capacity would be 500. So the ratio, like I said, the ultimate capacity of the pile group will not be equal to the n times the capacity of one pile. So therefore, let's say the group capacity is 450 and the total is 500, the ratio is called the group efficiency. So this will be roughly this will be 90% as a group efficiency factor. So it is very rare that you could achieve 100% efficiency in this group pile effect. And then this group efficiency factor is dependent upon number of pile rows we have, number of piles we have per row, the spacing, and the diameter of the piles in that group. And I'm sure you must have found these definitions and these factors in the textbooks that we have gone through in our good old days in the school. But these are pretty significant when you are dealing with the realistic problems. And in order to find the optimal solution, like I said in the previous slide, you have to optimize how many piles you need, what should be the spacing, what diameter should it be, what should be the thickness of the pile cap, etc., etc. So it's not as simple and easy as it sounds. Now let's move on to the next set of deep foundations or piles, which is called piled raft foundations. Now these type of foundations are becoming more and more common and popular these days, but let's go to the basic definition of piled raft foundation. So as you can read from the slide, piled raft foundations provide an economical foundation option for circumstances where the performance of the raft alone doesn't satisfy the design requirements. Under these situations, the addition of limited number of piles may improve the ultimate load capacity, the settlement and differential settlement, and the required thickness of the raft. So this definition was coined almost a decade ago. And after that came the high-rise buildings, where the superstructure and substructure interaction became so important that the raft became an integral part of the superstructure, and therefore we no longer limited ourselves to these limited number of pile definition. Now you can add hundreds of piles under a raft. And let's see what are the advantages of pile raft foundations in that case. So first of all, pile raft foundation limits the absolute settlement and the differential settlement because it is more uniformly supported all throughout. There are ambiguities in the soil stratas. So the pile raft foundation helps you in controlling these settlements. Then it leads to the reduction in the foundation tilting, which could be due to load eccentricities or irregularities in the subsoil. And it leads to the reduction of the raft internal stresses. Like I said, now the raft is more uniformly supported all throughout, so there are less or short unsupported lengths. Therefore, the stress concentration is not that much, and it is more spread out over the raft. And this has made possible to have rafts as deep as 15 to 20 feet, and having hundreds of piles underneath it. So let's check out the design philosophy of the pile raft. The main objective of the pile group design is to ensure that the foundation does not undergo excessive displacement, and this is called the serviceability limit state. Then additionally, often a factor of safety against collapse of the pile is required, and this is called the ultimate limit state. Now, depending upon the code of practice and the standards that you're using, you sometimes need to check both the serviceability and the ultimate limit state for the design of the pile. And most of the times, in order to capture the real ultimate state, you must consider the interaction of the foundation with the superstructure. And this ultimate limit state then reverts to a displacement criteria that is determined by structural considerations. So here, as you can see this definition from Randolph, it makes it clear that for pile raft foundations, in order to determine the overall settlement, which is the most important criteria for pile raft foundations, we have to also account for the ultimate limit state, which is a resultant of the structural considerations. And this means that we have to consider the superstructure-substructure interaction while designing the pile raft foundations. So let's see what is the behavior of a pile raft foundation. So behavior of pile raft foundation is much more complex than a single pile or a group of piles. So let's see why. So here you see we have a raft that has certain load on top of it, and then we have a certain set of piles. So if we just go by simple mathematics, we'll see that the total bearing capacity of the pile is actually a summation of the bearing capacity of the pile plus the bearing capacity of the raft. And the pile bearing capacity, as we saw previously, is actually the summation of end bearing capacity plus the skin friction capacity or shaft resistance. Whereas the resistance or the bearing capacity of the raft is actually the integration of the contact stresses with the contact area of the raft. And if this overall or the total bearing capacity exceeds this factor of safety times the applied load from the superstructure, then it is a good design. So it sounds very simple and straightforward in approach, and it seems like you can just pick up your calculator and start calculating it. Well, let me tell you this. You can do that kind of approach either using PY analysis or hand calculations for your single pile or group of pile behavior, but not for raft foundations. Let's see why. So here you see we have this thing called interaction that makes it utmost necessary to incorporate the real constitutive material models from to represent different types of soil strata and consider the soil structure interaction more deeply. So what kind of interactions we have here? You can see we have a pile soil interaction, we have pile to pile interaction, we have raft to pile interaction, and we have pile raft interaction. So basically we have 4 different types of interactions that you need to consider while designing the pile raft foundation, and thus it makes it utmost necessary to perform a full-blown 3D numerical analysis in order to obtain the true behavior of your pile raft foundations. As I mentioned previously also, that pile raft foundations can have hundreds of piles under their raft, and the cost of foundation would definitely go up if you have too many excessive piles. So it is again strongly recommended to perform a numerical analysis in order to capture these interactions to optimize your pile raft strength and behavior. So let's see a relative mapping of the behavior of a single pile, pile group, and pile raft. This will also help you in understanding is how pile raft is behaving and how we estimate the strength of it. So if you see, this is the standard resistance versus displacement or the settlement graph, and as we all know, beyond the bearing capacity of the single pile, we see a sharp failure, and this failure is usually called as uprooting of the pile, because the friction resistance is completely lost and the pile is fully mobilized, so it can go in or out very easily. It is not resisting any force. Then we have pile group effect, which goes to show relatively better behavior because the stiffness has gone down, and it can resist more loads, obviously because there are more number of piles underneath now. But still, beyond a certain limit, you see the same uprooting failure. But contrary to all this, if we see the pile raft behavior, we see that the stiffness has gone down because there are several pile elements, so it's more flexible arrangement or system. But what you should note here is that there is no failure whatsoever in pile raft foundation. So the secret of pile raft behavior is that it reduces the stiffness of the pile group on one hand, and on the other hand it increases the bearing capacity of the entire system. So therefore, pile raft foundation is able to sustain more loads without going into excessive settlement or relative settlement, and yet transfer the loads from the superstructure to the stable strata underneath it. I think this particular slide will make my point more clear as why you need to analyze this pile foundations or pile raft foundations in 3D. Now this is a simple problem. If you look at this as a group of pile, then you see the behavior of the pile at the corner is very similar to a single pile element. Then when you look at the piles at the edges, where you will see the effect of other piles adjacent to it, you'll see a slightly better behavior than the corner pile. But if you see the interior piles, which are surrounded by piles on all other sides, they behave like a pile raft foundation pile. So therefore, if we increase the number of interior piles, we'll have a much better behavior, and these piles would govern the behavior of the entire pile foundation because they are more in number. Now, if you're doing this analysis in, let's say, using py curve, then you will always be limiting yourself with this corner pile scenario to the best. If you're doing a 2D analysis, that means analysis in 2 dimensions, you'll only be able to capture one plane of your raft foundation. You'll be able to capture just the effect on the edge piles due to the effect of the neighboring or adjacent piles. You'll never be able to capture the pile which is surrounded by piles on all other sides. For this, you need to perform a 3D numerical analysis to achieve the same. Then let's move on to the design requirements for the pile raft foundation. So as I mentioned earlier, SLS or serviceability limit state is the decisive criterion for the design of vertically loaded pile raft. The magnitude of absolute and differential settlement and the tilting of the building are therefore of special importance, and especially when you're dealing with a high-rise building where you don't want relative settlement to occur between the towers or the buildings to sway and hit each other, or if you have a high-rise building that is tilted and then you have a strong lateral wind load onto it, it will amplify the effect onto the foundation. So since we cannot afford to have these kinds of settlements, the serviceability limit state is the most important criteria that you should meet when you are dealing with pile raft foundations. So this brings up the question that what should be the relative proportion of the load that is carried by the raft and the pile? And you should also be thinking that which pile configuration, that means number of piles, pile length, and the layout, would actually reduce the absolute and differential settlement and the structural forces most efficiently. And this is where I would like to lay emphasis on numerical analysis, and that too in 3 dimensions, because you'll not be able to capture the pile raft behavior unless you are doing a true 3D analysis. So now that we understand that numerical analysis is the way to go, we have to answer a couple of questions or find out what are the requirements from your numerical analysis model. So as you can see here, the model should be able to consider the three-dimensional behavior of pile raft foundation. It should be able to simulate the behavior of a single pile to check its reliability and adjust the applied parameters depending upon the chosen pile type. So this means before blowing up your model into full 3 dimensions and all with all the pile members, we should first make a 3-dimensional model of single pile, verify its results with the field data, and then apply those parameters to a 3D analysis model. Then the second most important requirement is that the applied constitutive laws should be taken into account, and those laws should consider the nonlinear pile soil behavior at pile shaft and pile base, and the stress strain behavior of the soil depending upon the applied stress path and strain levels should be considered. So basically this constitutive material model holds the key to the soil structure interaction. It should be able to, on one hand, capture this interaction properly. At the same time, it should also capture the complex behavior of the soil strata. And the applied model should be able to consider all the different interactions that govern the pile raft behavior. So like I said, we have pile soil, pile raft, raft soil, and pile interactions in raft foundation. And that is something that needs to be considered, or your model should be able to capture all these effects correctly. So let me walk you through the pile raft modeling process, or how you design raft piles. So you start with a numerical model where you will have a 3D model of a single pile element first, and there you will use all the geotechnical test results and the pile test results in it, and run a simulation with that single pile element. While doing the simulation, you will calibrate your results based on the field test data that you already have. Now this will call for certain iterations till you calibrate the behavior of a single pile in that numerical model. Now from there you can develop a full-blown 3D model where you have all the pile elements with substructure, superstructure together based on the parameters you obtained from the previous analysis. Once you have obtained the numerical model in 3 dimensions, you perform the simulation, and there you have to perform a parametric study, which means you can play around with different pile arrangements, different types of piles, different pile material, different dimensions, different lengths of the pile, and also apply different load combinations. Based on this parametric study and load combination, you will get a set of results which will be in the form of stresses, deformations in soil strata as well as in the pile members. So based on those forces and results that you obtain from the simulation, you have to check based on the code's standards whether the pile foundation or the pile raft foundation is meeting the serviceability limit state requirements and the ultimate limit state requirements. And this part of the job is performed usually by structural engineers. So you give them these parameters or the results which are used as a parameter for the structural engineers to design the cross section. And sometimes these cross sections are subjected to certain limitations from the field or maybe from other parameters. Maybe the client has laid some constraints. So the structural engineers can then suggest an alternate which geotechnical engineers must be able to put it back into the numerical model and confirm the finding. So this there exists a back and forth between the geotechnical engineers and structural engineers for the information of piles. I hope everyone has understood this particular chart. Thank you. Now let's move on to the summary of chapter 2. So the single pile design needs estimation of bearing capacity, settlement, and lateral behavior. For lateral behavior, PY analysis and numerical analysis are commonly used. Numerical analysis has certain advantages over PY analysis as it saves iterations and approximation. Pile raft foundation limits absolute and relative displacements or settlements. It also prevents tilting and reduces raft stresses. Pile raft foundation reduces the pile stiffness and increases the bearing capacity and thus prevents the uprooting failure or where the complete pile system is mobilized. The governing criteria for the design of pile raft is the settlement or SLS. Pile raft foundation behavior involves pile-pile, soil-pile, raft-soil, raft-pile interaction, making conventional analysis completely obsolete. Hence, a 3D numerical analysis should be performed and it is must for pile raft foundation. And last but not the least, numerical model thus created must be calibrated with field data and constitutive laws must reflect the interactions correctly. So this summarizes chapter 2 and now we'll move on to the second set of quiz. The instructions will be given next to the question, so read them carefully before attempting them. The duration is 5 minutes and the number of questions is 3. 30 seconds to go. So we have three pile modeling methods here. First is solid element modeling, second is beam solid connectivity, and third is line to solid interface model, which is also called embedded pile model. So let's take up each one of these modeling approaches individually. So here you can see, as the name suggests, solid element model. It has a model where the soil is modeled as solid elements and the pile member is also modeled as a solid element, and therefore there is an interface between two solid elements from soil and pile, and this has to be a 2D interface because when two solids are touching each other they are sharing a face, so therefore we have a surface as the interface. So if you take this thing little in more detail, you can see that we have a surface interface between the two solids. So this means that wherever we have the common node, there we have a surface where the behavior or the relative movement of these two nodes will be determined based on the interface between them. So I'll not go into too many details for now. I'll rather focus on the highlights that you should take from here. So for this type of modeling, the model definition and mesh generation could be elaborative for large number of piles. Now if you are dealing with pile raft strata, then you would have several hundreds of solid elements for soil itself, and then you will have several hundreds of piles, and each pile will be made of several hundreds of solid elements. So therefore the modeling will take really a long time, and then if you have so many elements in your model, the computation time will definitely be long. And at the end of the analysis, since everything is in solid, and when you look at the results, you always get stress values. So extracting the results for pile forces and moments are not directly available. So you first end up with stress values, and from the stress values you have to compute the structural forces. And like I mentioned, the interface behavior is represented by the surface between the two solids, and that surface could have different properties. So it could be elastic, non-elastic, Mohr Coulomb, and user-defined behavior. So this is one of the advantages of having solid-to-solid modeling, that the interface more properties you can control as per different uh, material models. Now let's see the second approach, which is beam solid connectivity model. Here we have the model that has soil model as solid. We have a pile or beam element to model the pile, and there is no interface whatsoever. So this means that my pile member here, which is modeled using a beam, is directly sharing the node with the soil strata. So between two nodes on the soil strata there is a pile member, so the relative displacement is superimposed based on the stiffness of the pile and the solid strata, and therefore if this displaces by x, the pile will also displace by x. Now this is not the true behavior of pile-soil interaction. There is a relative slipping between the two, and that cannot be captured with this modeling approach. Therefore this leads to highly conservative results. Whereas in the previous example, where we had solid-to-solid modeling, it was too detailed in order to achieve that, and this is completely, I should say, ripping off the value of numerical analysis. So the point to be noted here is that the nodal compatibility requirement makes the geometric modeling and the meshing of soil an elaborative process. So first you have to do the meshing of the soil, and then when you apply the beam element, you have to maintain the nodal connectivity one by one as you go down the length of the pile. And the second point is that for pile raft, where we have large number of piles, this technique will produce really large models and thus long computation time. The computation time here might be less than the previous approach, but a modeling process will make it overall so complicated that this model is not really preferred. So what is the use of investing so much time in generating this type of model, and then at the end you end up with results that don't represent the true behavior? The advantage of using this particular method is that you are able to extract the forces that you need in the piles directly. So since it's a beam member, you'll directly see the bending moment diagrams, you'll directly see the axial forces in the member, but they will be approximations. And the only reason we adopted numerical analysis is that we want to get rid of the approximations. So therefore, this brings us to a third approach, which is called line to solid interface modeling approach. In this model, the soil strata is modeled with solid elements as the previous two methods, but the difference is the pile is actually modeled with a special type of element, which is called embedded pile element. This embedded pile element has the property of pile or a property of a beam to give you the structural behavior of the pile, so that when you're looking at the results you can extract the bending moments and axial forces in the pile. Whereas in order to capture the soil pile interaction, we have an interface that comes along with this pile membrane. So this interface is also known as shear interaction between beam element and the surrounding soil, and you can read more about this approach in this following or mentioned paper. So let's see what are the advantages of having this line to solid interface. So let's see, this is one of the soil strata where we have modeled it with solid, and then we have a beam element or a line element, or in this case I should say embedded pile element stitching through. Similarly in this example and similarly in this example. So the outer represent the soil strata and then the line represents the embedded pile. Now the advantage of using line to solid interface is that you need not worry about the nodal connectivity. So this means pile and soil geometries and meshes could be done independently. So once you have modeled this geometry independent of each other and then you do the meshing, the program will automatically create nodes as per the meshing of the neighboring strata onto the embedded element, or based on the embedded element onto the adjacent or the surrounding soil strata. So in this way it makes the modeling process very easy. Secondly, the intersections of soil and the line elements are calculated automatically. So as you can see, this element is starting from nowhere from the surface, and there were no nodes on the adjacent edges of the solid. When you do the meshing, the program will automatically identify that this is the point of intersection of the solid with this line element, and therefore it should have nodes here in order to get a refined meshing. So these types of considerations are automatically incorporated when you're using line to solid interface using embedded pile elements. And the nonlinear friction slip properties for line solid interface elements are also available. So like I said, this line element or embedded pile element is a combination of beam and the interface together. So then you can control the soil structure interaction or soil pile interaction by defining the properties for that interface, which could be nonlinear. And later on, when you are doing the analysis, most of the times you will encounter this situation where you have to refine your meshing. You have to change your mesh size, and if you are dealing with solid approach or beam solid approach, trust me, it will be one of your worst nightmares, because it will take you so much of time to go in and delete everything and create it right from the beginning. Then it'll never you'll never be able to finish it on time if you have some last minute changes. This is not a problem with the embedded pile element, because you don't have to worry about the meshing, and it can be done independently for solid as well as for the pile member. You can at any time change or rearrange the meshes that you need for refining the analysis. And therefore, since we don't have several elements, we are just representing the interface and the beam with just one element, we reduce the number of elements in the model, and thus the models are lighter, efficient, and when you analyze them, they take less computation time. I hope the three approaches are clear, and we can move on to the verification of the analysis results. So once you basically any of these approach could be confirmed based on the analysis results verification. For this, we must perform the field tests, and here is an example of the field test that was performed in 1974 for a bridge foundation in Germany, and this test is still valid for the foundation projects today. So the setup was very simple. They had a pile member. Under the pile, they had set up the load cells to get the end bearing resistance, and they had sensors all around the periphery of the pile to capture the skin friction and the relative settlement between the pile and the soil. And then they were able to plot the three lines as you can see on this graph: base load, skin friction, and total load. Now we know that most of the time when we are dealing with pile foundations or deep foundations, we analyze or lay our decisions based on the skin friction value, because not every time we are able to perform the base load test on the piles. So, but if you are dealing with the pile which is strictly end bearing pile, then this becomes more critical. So once you have obtained this field test data, then you have to calibrate your model based on the data. So here you can see the similar setup when simulated in a numerical analysis model. We plotted all these graphs and found that they are following the same trend or pattern. So you can see this is the base load test, and the one with the dot is from the field data, the one with the straight line is from the numerical analysis of a single pile. Then you can see it's same pattern for skin friction graph and same pattern for overall or total behavior of the pile. So these tests have been performed, verified, and you should calibrate your model based on this field tests. So if you have performed these tests in the field, like here, then you should create your model and run the model and find out these results and compare them with your site data. If they are not matching, this means that you have to manipulate or calibrate your model by changing the constitutive material properties, by changing the material properties, and comparing the results by controlling the interface properties. And this is what you can obtain from pre-wire analysis and FEM analysis. FEM means numerical model or finite element analysis, and you can see that these curves are matching. From this simple analysis of one pile analysis, you can then go on to a more complicated analysis with several number of piles put together and capture the results for the same. So basically the comparison of FEM with PY analysis is also important at times, because you have to calibrate your model with the realistic data, and sometimes the realistic data could be erroneous, so you have to be on your guard based on the field sets results and the results that you are getting. So things that needs to be considered in numerical analysis. So these are the questions you should ask yourself before picking up any approach. So I told you there are three different approaches. Each approach has its advantages and disadvantages, and based on what you want to achieve from your model, you should go with the approach that fits you the most. By approach, I also mean if at all you have to do a numerical analysis or not, if PY will suffice, or if Brom's method is sufficient. So all these questions will help you in finding the ideal approach for your project. So the questions are something like goes like this: what is the most important behavior in your model? Ask yourself whether it is the behavior of a single pile that that is of prime interest to you, or it is the behavior of the group pile, or there is a very high axial or lateral load onto the pile, or is there an adjacent structure or superstructure that you have to consider, and how complex will be the soil structure interaction in this soil strata. So once you find the answers to these questions, you can then narrow down to the approach. So let's say the answers to the first one was behavior of single pile is important for calibrating my model. Okay, but I'm dealing with pile raft foundation, so therefore it's not just a group effect, it's a bigger picture. And if since I'm dealing with pile raft foundation, I'll expect huge axial force or vertical loads onto the pile, so definitely I must go with a 3D analysis. There could be an adjacent structure that could affect, but definitely the superstructure behaves integral to the raft, so therefore I must consider the loads that are coming onto the superstructure because of the connectivity with the raft. And soil structure interaction is very subjective. You can be working on very stable soil strata, but since the vertical load is very high, you have to go with the pile raft foundation. That's one. Or your soil strata is very weak and therefore you are subjected to use pile raft foundation. So under these different situations, you can make a more informed decision as what suits your model the best. And a set of secondary questions that you should ask once you have finalized that, okay, I want to go for numerical analysis. The questions that you should answer yourself is, what is more important in this analysis? Is it the accuracy or the efficiency that matters? And most of the time it is a difficult question to answer, because engineers believe that if I am doing a numerical analysis with everything in solid elements, I'll get a highly accurate model. No doubt that's true, you'll get an accurate model, but it'll take so much time to model and so much time in extracting the results that you will not be able to justify your efforts in the output. So this type of question should be answered very efficiently. And from our experience, I would recommend the use of embedded pile elements, which have shown to give better results over other approaches. Therefore, it is very important that you have an efficient modeling setup that will reduce your analysis time. You can use different sets of materials and elements in this combination to get a good model with efficient run and accurate results. So this brings us to the summary of chapter 3. So there are 3 pile modeling approaches: solid-solid, beam-solid, and line-solid. The line-solid approach is also known as embedded pile approach, or it uses special type of element called embedded pile. The embedded pile approach has a beam element to represent the pile member and a friction or tip bearing interface element to represent the pile soil interaction. The advantages of using an embedded pile element are: pile and soil geometries and mesh can be generated independently, intersection of line and solid elements can be calculated automatically, and nonlinear friction slip properties can be accounted for through interface elements very easily. And thus, the models that are generated from this approach are lighter, efficient, and take less time to run. The numerical analysis model must be verified with the field test data of a single pile prior to generation of complete group or pile raft model. And the selection of modeling approaches depends upon the objectives of your analysis. So now it's the time for quiz number 3. Again, the pattern remains same. It has 3 questions, 5 minutes. So I'll launch the quiz now. Good luck. last 1 minute. All right, thanks for submitting in your answers. I hope the test was simple enough. Now let's move on to the last part of the session today, which is case studies. And we'll be covering two case studies today. One will be of luxury apartment foundation, and the other will be for a high-rise building foundation. And in this case study, I'll try to emphasize and answer the questions which were similar to what I asked you in the uh, previous chapter. So let's say this is the project. These are the luxury apartment in Barbados, and as you can see, the total project value is £50 million. The site is 225,000 square foot, which means this is a very wide spread apartment building. And the location of this site is very close to the beach. Therefore, the soil strata is not very stable, and there they had to go for a pile raft foundation because of its soil strata conditions. And although the load from the superstructure was not that significant, and it could have been dealt with different set of group pile arrangement, but since the soil strata was not stable enough and it was a very flat structure, so they decided to go for pile raft foundations, and they were interested in raft settlements, pile forces and bending moments, and stress and strain levels. So therefore, they had to use embedded pile element approach. So this will probably explain the picture more clearly. You can see it is surrounded by water. On this side it's a beach area, so therefore you have to take care of the load and the load, how it is transferred to the stable stratas underneath. And as you can see, it had a non-symmetric, or I should say asymmetric layout. So this means the load distribution would vary based on the raft area also. So hence they could not do with just a 2D analysis, because if you have to do a 2D analysis, then you would have several sections that you need to analyze it, and you will not be able to capture the out of plane effects. So hence a 3D numerical analysis model was used for this project to determine the results in pile members and the raft members here. For this application, Midas GTS was the software that was used. And the next case study is of the high-rise building, and this is in Dubai. And it had several tall towers. Like you can see 4 tall towers, each of them at least 50-story high. And then they have these podiums and adjacent buildings in its vicinity. So it became very essential for the engineers, instead of going for individual foundations separately, they have to consider the effects of the adjacent structures, or if they are drilling these deep foundations, what would be the stresses coming on to the foundation of the adjacent structures. So they had to model the adjacent structures onto the same raft for these raft foundations. And as we talked about this previously, it's a high-rise building. It will have huge wind loads or lateral loads effect, and this again calls for a raft foundation. So irrespective of the soil strata here, the loading condition and the structure type and the field conditions forced engineers to use pile raft foundation, or I should say pile raft foundation was the optimal solution for the engineers dealing with this type of project. So they wanted to find out what is the raft settlement, which is pretty straightforward. I mean, which is given output. Then they need to find out what is the pile lateral deflections because of the heavy lateral loading, and then raft forces and bending moments because they have to design the raft, as well as pile forces and pile bending moments, and not to mention uh, soil stresses and strain levels in the soil. So here you can see this is the top view of the pile raft foundation here, and if you see from the side view from the north and the east, you will see the pile members are of different lengths, and this type, and even though they are in same soil layer, depending upon the superstructure load and the interactions, you can choose to cut short your piles or lengthen them to a more stable strata. So this is a type of optimization that you need to do, and you will be able to do if you are working on a 3D model where you can capture the strength and the effects of neighboring pile members. So in this numerical model, another thing that you should note here is that the podium and the basement levels were also modeled in the same structure. Because it is an existing structure, they need to find out before constructing this type of building what force is this existing structure or the podium level is exerting on the pile raft foundation, and how much would it affect the stability of the soil existing. So this is the side view of the piles and the basement together, and this is how the results were extracted. You can see the settlement results from the soil solid data. Then we had I think solid elements were used to model the raft. You can either use solid or plate elements depending upon your needs, but the bending moments were directly extracted from the raft. The vertical stresses were easily excuse me, were captured based on the soil strata and the interaction of the pile and at the pile tip. And since they had used embedded pile elements, they defined the different interface for the tip and different interface for the pile itself. And due to enhanced visual aids of the popular software available these days, you can visually verify the results whether the piles are getting mobilized or they are transferring the force correctly or not. And with embedded pile elements, you can extract these kinds of pile axial forces. Now, for those who are wondering what software has been used for this project, I would like to share Midas GTS was the software used for this project. So this brings us to the end of our session today. Thanks for joining in. I will be more than happy to hear your feedback and questions about this session. If you have any questions, comments, please feel free to share with me. You can reach me at my direct number, which is 646-852-9292, or you can email us at midassoft@midasuser.com. And before I close the session, I would like to share the upcoming session, which will be aired on September 4th, 2013, and the time is 3 p.m. Eastern Standard Time. The topic is Design Solutions for Projects that Require 3D Modeling and Analysis. So like today we covered why numerical analysis is useful or needed in foundation design and what type of foundations. In that session, we'll be talking about the fundamental concepts of 3D numerical analysis, what are the benefits of 3D analysis, and we'll cover all different type of geotechnical projects that could benefit from 3D analysis uh, in different platforms. So this is all we would like to share with you today. If you have any questions or comments, I can take them now. Alright, so we have one question here. How, or there are multiple questions. Okay, let me take them one by one. So one of the question is how to connect embedded line element to solid element to the solid element of the raft slab. Either it is a pin connection or moment connection. Now I understand where this question is coming from, because we have been so used to do analysis in software like LPile or I should say BPR. We always have to simulate this pile cap or connection with the superstructure or the raft by simulating if it is a complete fixed connection or it is a flexible connection. And that is the whole reason that in order to take you away from those kinds of approximations, we do numerical analysis. What we do is we have a complete nodal connectivity with the elements of the raft to the elements of the pile or the line element, and we don't apply any kind of restraint other than the soil strata around it to support it. And therefore we are able to truly capture the interaction between the raft and the pile, and raft and the soil, and raft and pile and the soil. I hope that answers your question. Then another question coming in here is that there are different approaches available: PY analysis for lateral behavior and numerical analysis for lateral behavior. What type of analysis is applied in which type of software? So I will answer these questions later on independently to the engineer who are asking these questions, because we will not be marketing or publicizing one software over another. So I got your question. I have recorded it. I'll definitely come back to you. There is one more question coming in. How do you control the excessive settlement of the pile foundation? So are you asking about single pile or pile raft or group of pile? Pile raft. Okay. So basically when you're dealing with pile raft foundations, there is nothing that you control the settlements with. It is always the optimal length of the pile members that you need to obtain, so that the skin friction that you have can take care of the settlement of the shaft. And now when there are so many members in the adjacent to each other, they completely behave like a one assembly, and then they control the settlements. Now after your analysis, it might be a possibility that you get excessive settlement over a certain set of piles as compared to others. This is called relative settlement or differential settlement. So in order to fix that kind of problem, what you can do is you can make the pile elements where you are getting excessive settlement longer than you initially started with. Once you make them longer, you add more area to your pile. It'll increase the skin friction of the pile, therefore it will improve its behavior against the settlement. And secondly, if you are not hitting the hard strata yet, then it will bring you closer to the harder strata, so that the stresses can be easily transferred, or you can get enough end bearing resistance from there. I realize we have exceeded the time limit by 15 or 16 minutes. So I'll close the session now. If you have any more questions, feel free to write to us and we'll be more than happy to answer them. This is Arun Sharma from Microsoft signing off. Have a great weekend ahead. Thank you.